Really briefly, I want to talk a little bit about one real satellite, which is in a more or less a circular motion around the Earth, and that's the International Space Station. So the International Space Station is not in a perfectly circular orbit. Again, real things typically orbit in ellipses, and so the distance to the Earth actually varies a little bit. Right? So if this was a circular orbit, this would be a fixed value. Here it's not. So it's a little over 400 kilometers. The orbital period, so the amount of time that it takes to complete one orbit, is 92.65 minutes. Yes, these values did come from Wikipedia. There are some values in the book that are derived for a similar situation, but are not actually exactly the same as the ISS. So the orbital period is an hour and a half. Think about that. It goes around the entire Earth in an hour and a half. It takes a plane like a day to do that. So clearly it's going really, really fast. How fast? Over 7, almost 8 kilometers per second. Right? So before, when we calculated that speed necessary, it was a couple of kilometers per second. And similarly, the ISS is going many kilometers per second. So this is incredibly fast. Now, one thing that's really important to point out is that the force of gravity up here is 90% that of the surface of the Earth. And the reason I say this is because when you see pictures of astronauts at the International Space Station, they're floating around. And the situation at the International Space Station gets referred to as microgravity. There's very little gravity. That's actually a misnomer. It's not true. The force of gravity is almost the same as on the surface of the Earth. It's 90%. The reason that the astronauts are floating around inside is that the astronauts are in freefall. The ISS, the big metal part, is also in freefall. That everything up there is traveling at the same speed and it has the same acceleration. So this is where it's helpful to go back and think about the difference between mass and weight and gravity. That if I'm standing on a scale in an elevator that is accelerating downwards, that scale will read a smaller value than if I'm standing on stationary ground. Similarly, within the ISS, everything is falling at the exact same rate. That means if you tried to stand on a scale, well, the scale would read 0. That gravity is pulling everything down into an orbit, right? Again, special case of projectile motion with the same acceleration. So the force of gravity is not 0 at the International Space Station, it's just that everything is falling at the same rate relative to one another. So please be careful about that. And again, this is a nice picture. The International Space Station is really, really cool. Perhaps because you've grown up with it, you don't appreciate how amazing it is that we have a thing in space. We built a thing in space that people live on for an incredible amount of time. And there's an even cooler picture I want to show, which is during the ellipse. So these are time-lapse photos of the space station, and then these are just sunspots. So these things are just sunspots, don't worry about that. But so during the eclipse, when the moon, right? So this is the moon passed in front of the sun. I bet you know that it's this one. That the ISS actually happened to flip by, and it was going very fast. So I don't know the actual time lapse taken between these pictures, but this delta t would not be very big. If I was good at astronomy, I could actually use the size of the sun and the distance of it to actually calculate it. It's just geometry. But there were a lot of pictures that people took of the eclipse where they saw the ISS in front of it, and that was pretty cool. So you can actually see the ISS from the Earth, and if you know where it is, you can especially catch it. I think in the evening it's sometimes really easy to see light glinting off of it, but it's a little bit hard sometimes in that it is so small with your naked eye you might think it's a star, but it's a really, really, really fast-moving star. But it is distinguishable from an airplane because it doesn't have like pulsing blinking lights. So you can see the ISS with your naked eye, but you kind of have to know what you're looking for, when to look, and where to look. But keep in mind, it passes by every 90 minutes. So to summarize the important things from this video, which again was largely a case of applying our previous ideas to the case of orbits. So circular orbits are a special case where we've taken projectile motion, we've thought about the horizontal speed being so very big that the curvature of the Earth actually starts to matter, and eventually the curvature of your projectile is the same as the curvature of the Earth. For this, gravity is providing your central force. So it's a circular orbit, meaning your radius is the same everywhere, and our central force, gravity, points in the r-hat direction, which is towards the center of the circle. Finally, I went on perhaps slight tangent that the International Space Station is really cool, but I pointed out that gravity still exists there, that the International Space Station is going in an orbit around the Earth very, very quickly due to the force of gravity. If there was no force of gravity there, it would not be going in a circle. And the gravitational force there is about 90% what we experience on the Earth.